Hi everyone, and welcome to our BlackHat talk. My name is Michalis Magnatakos. I'm an associate professor of computer engineering in New York University in Abu Dhabi. I'll be virtually joined in a few slides by Dimitris Tichalas, who's currently a PhD candidate in the NYU Tandon School of Engineering. And this talk will be about industrial control system security. Industrial control systems, as the name implies, are systems that are controlling industrial equipment. They interface with the real world, they receive some input from a sensor, they produce some actuation, and the systems that are hardened to withstand extreme operating conditions. In the slide, you can see a few slides of PLCs and SCADA systems. PLC stands for Programmable Logic Controller and is a major component that we'll discuss today. ICS are important because they are major components of critical infrastructure. Critical infrastructure is power grid, communications, nuclear, dams, wastewater systems, anything that the country relies on. And as you can clearly understand, if things go bad in ICS, then things can go really bad in the real world, from destruction of equipment to even human injury or deaths. ICS have been changing, have been evolving. It has been named Industry 4.0 or Industrial IoT, same name, same, and we're ditching something like this to go to something like this or that. In other words, you're moving from more electromechanical components to more digitized, computerized components. So ICS nowadays look more like typical computers. They have third-party SoCs, you have regular microprocessors in them, ARM, x86, you have a network stack, you have a general-purpose operating system, Linux, Windows, and also you have advanced connectivity capabilities from FTP to even TCP/IP to connect to the internet. So as you can clearly understand, since ICS are now looking more like computers, then every attack we can do on a regular computer can now be ported to critical infrastructure. From buffer overflows to privilege escalation, spoofing in the network, all the options are there for us. And not only we have more attacks ported, we also have more access points because of this connectivity, the advanced connectivity to ICSs. We have this IT-OT convergence that we have more connection from the enterprise business network of an organization all the way to the process level that connects to the sensors and actuators of the physical process. So security is important, and it becomes way more important nowadays because ICS have been traditionally developed for robustness and not for security. Most of the within the life cycle of the ICS, we focus mostly on safety, and security has been a much newer component that we have been addressing lately. At the same time, ICS have long shelf life. They're once installed, they stay for 10, 20, 30, 40 years. So unless you have a proper mechanism for updating them, they typically have outdated firmware, operating system, or versions of the software installed in them. Also, the PLCs would have typically limited processing power, a processor in the order of 500 megahertz, and memory in the order of 256 megabytes or 512 megabytes. So you cannot just load not on antivirus and call it a day, or advanced machine learning based intrusion detection systems. You have to find solutions that are proper for a PLC that it stays, it has to be online all the time, and it has limited processing power. Is it a real problem? You don't need me to motivate that for you. We've seen many attacks in the real world. You can find also many talks on BlackHat about it. And what I want to emphasize here is that we've seen some attacks, but also keep in mind that many times these attacks are not publicized for various reasons. So there must be many more we don't know of. So ICS security is a real problem, and we need solutions for it. So this is where we come in. We're trying to change this amazing paradigm of let's wait to be attacked and then we'll do something. We're trying to be proactive. Being proactive is not easy though in the context of ICS because the systems once installed, they cannot be modified. They're very hard to decommission, they're very hard to be updated. So the question we're trying to answer here in this talk is, Can we be proactive about security of ICS, but without affecting the PLC? And this is what we'll discuss in the next slides. So we propose 3 steps that we'll see individually in the next few slides. The first step will be to connect to the PLC. PLCs have local connectivity capabilities too, so you take your FTP cable, you connect to it, and then you download, you extract from it some files that are needed for step 2, which would be the emulation of the PLC. So you take all the files out of the PLC and you don't affect its operation because PLCs have this connectivity capability. You take the files out and you have another system, an external system, that you use the files to create an emulated instance of the PLC. Now you have a secondary PLC in a way running in a different computer. And now in step 3, you can fuzz that because you know fuzzing creates crashes, and of course we don't want to fuzz the real PLC. That's why we do it in the emulated instance. And that's exactly what this talk is about. Emulate a PLC and then fuzz the emulated instance in order to uncover vulnerabilities of the actual PLC. But if you fuzz the emulated instance, you don't affect the real PLC. And this is what we call Stuxnet-in-a-Box, because it dynamically, you just connect to the PLC and it will do everything else automatically. So this combination of emulated and fuzzing, I'm re-emphasizing that allows non-intrusive vulnerability assessment of PLCs. As an example, we'll focus on the Codesys framework. The Codesys runtime is an evolution in PLCs. It uses commercial off-the-shelf operating systems like Linux on ARM or x86 processors, and currently Codesys holds 25% of market share. Since this framework on the PLC is based on Linux, then we can bring all these amazing things Linux allows us to have, OpenSSH, OpenSSL, Apache, FTP services, SSH services, Telnet, and anything we need. There is a mature library waiting for us, so we don't have to develop our own. And now because of the fact that we bring in open source components, but at the same time we have our own proprietary components. If you look at the slide, we have our open source operating system, but this will run the proprietary runtime for the PLC, as we've been discussing. And this runtime will be written in standard code, C++, and compiled with a standard compiler, and will run as a process in the operating system. This runtime will have several threads, and some of these threads will be instantiating open source components like, again, some OpenSSL components or Apache web servers, or it could be having proprietary components like communication with Modbus, that's a network protocol for PLCs. And also, we're also having in one of the threads the main PLC binary written in a PLC standard language like ladder logic or structured text, that's using a custom compiler to do that. So you see, within that component, within the PLC, we have a mix of proprietary and open source, and also a mix of differently compiled binaries with regular compilers or with custom compilers that compile a different language like ladder logic. So the security question becomes even more interesting, assuming all these components that are coexist in a PLC. To give you an example of what's inside the runtime, here you see the boot process of the PLC, and you see the runtime being part of the boot process actually. And if you also see within that, you'll see that actually it runs as a daemon in the Linux operating system. The runtime itself instantiates many threads, as I discussed before. You can see some of them on the right-hand side of the slide. Like the Modbus we discuss, or would be the visualization task, the interface to the peripherals, or the main PLC binary task, that it is actually what the PLC should be doing, the main control logic of the PLC. And all these threads, as you can see on the left side, we actually focus on 3671 here, this one. And you can see that's the main PLC binary that is run in the stack, and that stack actually is executable. So anything you bring to the PLC to be, you bring it from the sensors, or you can bring it also from the network stack to the PLC binary, it will be loaded in executable stack. That means you can maybe bring your own payload and redirect the control flow to have remote code execution. And the security of the specific runtime, Codesys one, again, this is the future. We need all these components because the Linux library is way more mature than doing your own custom cryptographic implementations, for example, in case of OpenSSL. So there's a lot of research on the Codesys runtime, but at the same time, it's been a target for attacks, and we've seen more and more CVEs appearing. And you see how the numbers are wrapping up from 2 in 2017 to 21 reported in 2020. And some of them have much higher criticality. As you see the latest one, you can do remote code execution through some heap overflow in a web server. So it's not like things are getting worse in the framework, is that we have more of these PLCs and we have more people also looking at them. So we need to do something about it, and this is exactly what this talk is about. And with this, I'll hand it to Dimitris to continue with discussion on PLC Control Application.
Thank you for the pass, Mihaly. Now let's continue this introductory stage of our presentation by talking a little bit about the PLC Control Application and what it is, right? Now, the PLC Control Application is essentially control logic, like this here, made into an application, compiled into a binary, turned, if you will, into a collection of assembly instructions. Now, you can call it control application, control binary, PLC binary, etc. Now, this control application is being built, loaded, and executed via the Codesys platform. The building, that is programming, compiling, and debugging, happens with a dedicated Codesys API on the user computer, and the loading and execution happens with the Codesys runtime on the PLC, on the actual physical logic controller. There are many languages that have been standardized by IEC with which you can write a PLC control application, like ladder logic, for example. Many of you might be familiar with it. It's the simplest and most ubiquitous. Another one is function block diagram. Moderately complex, like ladder logic, but a bit beefier. And then you have structured text, which is a very complex language, and it's actually based on Pascal, and it might remind you of a typical imperative programming language with complex structures like arrays, like if and else statements, and for and while loops. And these structures can introduce vulnerabilities, as in typical programs which were not known previously, that can be enabled in control application. And let's see how. Now, let's say you have a program with a variable input. In PLC control applications, you have a sensor input, which is essentially a variable, and this input is used for indexing an array, for example. The compiler cannot predict that this is a thread because the value of the input is not known at compile time, and this might introduce an out of bounds read or write thread. Right, in this program, for example, you have the input, which is used as an index to this Snoop array. Now, this index can be a very large value, like 1,000, for example, or 10,000, or some large value with an even larger offset, with which you can use to access memory way outside the memory confines of this PLC application. You can use it to access other threads, other processes, or even the kernel itself, because remember, the PLC application ran within the Codesys process, which we've shown that is a daemon process, essentially. And you cannot just read, you can also write anywhere you want, in other applications, in other processes, in other threads, or on the kernel memory space. And also, you have third-party libraries, C-like libraries that have been developed to be dynamically loaded on the PLC control application and enable a low-level memory management facilitation. And they may lack bounds checks and enable bugs like buffer overflow. Now, let's see here a subset of these functions. You can recognize some names like string copy, memmove. We have checked these functions, and many of which lack bounds check on the inputs that they handle. And we have tested some of all of which, and some of them they conclude to crashes, which is an indication that the buffer overflow bug may be present. Now, what to do, right? The compiler has inherent weakness, as we've seen, and there are untested third-party libraries. Now, we have a second challenge because the PLCs, they are expensive devices. You cannot own a large number of PLCs just for testing. The PLCs are very slow, and also they must be perpetually engaged. You cannot just take a PLC out of commission and use it for testing. Now, the challenge for the first one is fuzzing. Fuzzing is dynamic assessment. Fuzzing can expose vulnerabilities that the compiler might have overlooked, and it can also be used to test for security these third-party libraries. And for the second challenge, you have emulation, which is essentially software abstraction of hardware, where we disengage from the need for the hardware device because we have a software instantiation of the device on our computer and do whatever we want with it. Now, fuzzing is essentially input testing with corner cases, right? The fuzzy outliers. You start with generating an input, you use this input to execute your binary, and then you analyze the system behavior based on this execution and log any issue that have arisen from the execution. The fuzzing process can be enhanced by input mutation, where you can have simple bit flips, half byte or byte flips, and also binary instrumentation, where you have your typical code and add some additional code which can provide feedback on the execution, for example, code coverage. Then you have emulation and powerful platforms like QEMU. QEMU can enable full system emulation, essentially replicating the whole function of a system like our PLC. With enough information from the PLC itself, we can build an image which QEMU can use to boot the whole system like it was an actual hardware device. What we can do with the PLC, right? We have many targets. We have system binaries because remember, this Codesys platform and our PLC application, they are being hosted in a Linux-based environment with binaries like bash, etc. You have the Codesys runtime itself. It's essentially a big binary which have been used for testing in the past, and many CVEs have been exposed plaguing this runtime. And also have the PLC application itself, which has never been tested as a typical software application, and we will have some fun with that later on. Now let's start with the system binaries and our platform IFSET, in-field fuzzing through system emulation, right? Our platform essentially connects to the PLC through SSH or FTP and gets an archive that contains a subset of files, folders, and configuration files from the Linux-based device, which we can use to extract necessary information like a kernel configuration or a file system. These are the only things that are needed to create a bootable QEMU disk image, which you can use then to mount for additional processing like modifying initialization scripts or adding binaries like the fuzzer. And then you can use QEMU to boot the whole system, log in through default credentials, and then, in our case, use AFL to fuzz system binaries. And let's see a demonstration of that. Now let's start the demonstration of our IFSET platform. This first step is actually automated, but for this demonstration, for the sake of this demonstration, let me show you how it's done manually. First, connecting to the PLC, and then navigating to this here folder and finding this script, this extract.sh, which is a script that creates an archive, this specific archive, which contains a subset of files and folders found on this device that are enough to make a QEMU bootable image, right? And let me actually run this extract.sh. And why I'm running it is to show if there's any effect on the system, because the IFSET platform is non-invasive, right? And let's see here, which is a live feed from the PLC. It's an HMI connected to the desalination process, to an industrial process that's running on the PLC at this point. There's some values from this process, input, output, set point, and as you can see, there's nothing really happening, right? There's no violent shifts in values. It's like there's nothing being executed on the PLC, which is actually the point. Now the extract is running, but the effect on the PLC is minimal to none. Let me stop this because I already have a copy of the star file here on my laptop, and let's make an image with this. And let's call it DHA underscore test. Let me make this a little bit bigger. All right. And the image has been created. It's here, this DHA test. And I can use the utility mount image to mount this image here on my computer. And essentially just open it up and see what's inside and maybe add something. You can see typical files from a Linux system, and there's a binary that I added, which is the AFL fuzzer that I will be going to use, a script which automates the fuzzing process, and of course, just a little binary that I put there to make sure everything works correctly. Now let's boot this image. Some feedback information from the booting process, pretty much some devices that have not been instantiated and they're just complaining, which I won't use for this fuzzing session. For this fuzzing session, I will just target some binaries that are found on the device itself, like bash, right? The bash instantiation, the bash binary on the device I just extracted is an older version one that has not been patched to the latest version and maybe has some vulnerabilities. Now let's log in. Let's go to the root folder and run my fuzzer script with bash. All right. This is a screen that many of you may recognize. It's AFL, right? And it's actually fuzzing the bash file, the bash binary that's found on this here system, on the extracted system. Now, what we care about is this one. And we just found a new crash. Let's stop this fuzzing process, clear the screen, and let's reboot the mounted image, because AFL cannot be stopped automatically on this emulated instance. I have to reboot. It's a little bit of a weird procedure. Now, the output of this fuzzing process is a file with a name based on the stage of the fuzzing that has caused the crash. In this case, I think it was Havoc, the number of execution that caused the crash, and then an identifier. This is the name, and the contents of this file is the actual string or the file or the input in general that caused the crash. Let me log in once more. Let's navigate to the folder out crashes, and let's see here the file. Right now, I can cut the contents of this file, and I can pipe it to bin bash and see what will happen. Nothing much seems to happen, right? But in actuality, the system has crashed. There's nothing I can do. The system is completely unresponsive, because you see, the input that caused the crash, when piped into bash, executes a fork bomb, which is let's call it a program that will constantly create threads and will take all the resources of the system, rendering it unresponsive. Now, if this would happen to an actual PLC in an industrial environment, this will make the PLC to be taken out of commission, rebooted, and then reinstated, which for an industrial process, this is a very dangerous situation. Now, the only thing I can do here is just terminate this procedure. So we've seen how we can perform security assessment on the system binaries that are found on our PLC, so we can have an idea of how secure the system is. Now let's see what we can do about the application, the PLC application, with our tool called ICS Fuzz. Now the thing is that PLC applications are not straightforward for fuzzing, right? Because their binary format is not suitable for fuzzing. They're not ELFs, they're not portable executables, they cannot be targeted by typical fuzzers like AFL. And the binary must exist in codesys context. It cannot be loaded and executed with some system call, for example, like a fork server or something like that. We can be a little bit more imaginative with that. And essentially, fuzzing can be broken down to two very important things: execution control and input control. Now, execution control, we got this handled because the PLC always run on a cycle, the so-called scan cycle, where the program reads some sensor inputs, is executed, and then updates the actuators with its output values. Now we can leverage this cycle for continuous execution of our program, which is pretty much what fuzzers do, right? And then we must see how we can enable input control. We must reverse engineer the input delivery to the PLC to understand how control is being delivered to the application, so we may find ways to control it, right? So let's follow the input. We have a sensor which gives data to the PLC I/O, which is essentially a fancy GPIO, which is then handed to a type of GPIO memory in the PLC, which is then followed to the K-bus memory, which is an inter-process communication protocol, which is then handed to the control application memory. And by choosing the most controllable point in this chain, we can find a place to force new values in memory by essentially replacing the input to be delivered to the application with our own input, essentially controlling the input ourselves as with any fuzzer. And we can mutate these values based on established schemes like what happens with AFL. Now, we can also have instrumentation because the thing is, if you don't have source code, you cannot do much, right? But we can scan for opportunities with the code we have, right? Let's see here, this code here. It's an excerpt from control application. You can see this instruction here. That's a NOP instruction. That does nothing, right? Can we replace NOPs with more controllable code, like the store instruction, which essentially logs the program counter to some memory address that we can have access to? Then we can have some feedback on the execution of this application, where we know where the execution has been traveled through and get some information about the code that has been covered. And now let's demonstrate our ICS fuzz platform in the context of the PLC HMI and see how it works. All right, now let's go ahead with the demonstration of our ICS fuzz platform. Now the program that we're going to be fuzzing is this one, right? Which is a pretty simple one. The output is getting its value from the output of this PID function, which in turn gets input from the actual input of the program, the input one, which is essentially an input that comes from a sensor. But our fuzzing engine that runs on the background is forcing different values based on a mutation strategy on this input value that we get to the program, which I will show you in a little bit how they pretty much change when this program running. Let's see the actual function, this PID. Now, what it does here is essentially just producing some kind of output here, but we have introduced a vulnerability from this function, this sysmemmove. Now, this is a counterpart to the memmove function that you can find in C programs, where one buffer is moved to another buffer based on their pointers, and the amount of data that is going to be moved from one buffer to the other is designated by this here variable. Now, in our program, this variable, it's getting influenced by the input. It's getting changed by the input, which again we control. So by fuzzing, by changing the input, at some point we will force this value to become large enough where this buffer will override this buffer and then override some more data on the stack, because this is a function that we're running here, right? And this value, for example, will be overwritten, this value will be overwritten, and some other value will be overwritten as well, that I will show you in a little bit. Now, this program has also been instrumented, and the instrumentation is essentially pretty simple, where this is a disassembly of the program that we are running. And you can see here this instruction, which essentially does nothing, right? So we are taking this instruction, we are replacing it with a store instruction that we are just directing to store the current program counter from the execution, and then we're just putting it in an output file. Now let's start with the fuzzing of this program. Right now it's running. You can see the input values, how they are changing based on the mutation strategy. Right, this is how the input changes. Let's stop it a little bit and show you what happens here in the stack that we have got from debugging. Now you can see here in this function you have the B's and the A's, right? 61 and 62 in binary. Now the 62s, they are the B's. This is the original buffer that's instantiated in the stack of the program, and these new 62s, these are essentially the buffer with the A's that has already been overwritten by the B's. Now the A's have been overwritten completely in their entirety, and there's some other values that have not been overwritten yet, like the deadbeef I showed before, the cafedef as well, and this one. Now this one is the return address of this function. Now when this return address gets overwritten, the program will crash, and let's see that happen right now. Again, the input is getting mutated, it's getting larger and larger, and at some point it crashed. And the crash you can see here on the HMI, it's this little yellow and red combination, and there's a red LED that's lighting on the actual physical device on the PLC. And let's connect to the PLC and see the output of this here program. All right. and you can see here what the fuzzer has logged here, right? You can see the inputs, and these are the values, the program counter values that are logged. These are program counters that have been stored with the instrumentation, and these essentially designate the points of the code that has been executed during these fuzzing sessions. And the last one is this one, where the input 5283, which we can also see here, has caused the crash of this binary. And this is pretty much how our ICS fuzz platform works. Now let's recap all this information that we uncovered for this assessment, right? We can reverse engineer the PLC application function and manipulate its functionality, as we've seen with understanding the input delivery process, for example. We can fuzz the PLC application for vulnerabilities, and we can exploit vulnerabilities, as we've seen in the previous demo with the buffer overflow exploit. And by combining this information, we can synthesize a new attack vector, a novel attack methodology that can manipulate a PLC application's functionality, and exploiting the vulnerability that we found with fuzzing, insert a kernel rootkit to spoof correct function, essentially combining the functionality of Stuxnet in just one application. And now let's see how this application is formed, shall we? Now this here is this application. You may recognize some parts from the application that we used for the ICS fuzz demonstration, where we have the sysmem-move, the vulnerable function that will essentially cause a buffer that is vulnerable to buffer overflows, which moves one buffer to another based on their pointers and on a set value for length of this movement. Now, in the ICS fuzz demonstration, we moved a vector with B's in the place of a vector with A's. Now, in this demonstration, we will move this here vector, this shell code, essentially, to a vector with B's. Now, the shell code starts with an obsolete, and it follows with hex code of some assembly instructions, which will do two things. The first one is execute a program that will alter the functionality of this PLC application, and the second one is the insertion of a rootkit that will spoof correct functionality to the HMI. Now, this HMI here is a live feed from this here application. You can see that it's showing correct functionality, at least what this PLC application does. The input is at around 550, the output is at around 820, and when this sysmem-move it will get exploited, this will get executed, the functionality will change, and the functionality right away will be spoofed. Now, for the sake of this demonstration, I will execute the program that changes functionality manually to show you its effect on the HMI, because the actual malware, the actual application that does both things will show nothing different in the HMI. You know, the functionality will change and it will spoof immediately. Now let's see a little bit about this program. All right, this is the operational meltdown. This is the program that will change the functionality, and let's see what's inside. Now this program finds a PID by name. It scans its memory space for patterns, and then it writes on the process, right? And the process that we choose, that will recognize its PID, is KBus cycle task. Now, KBus cycle task, if you remember from a previous slide, essentially implements the scan cycle. One of its duties is to deliver the input from the PLC I/O, a sensor, for example, to the PLC application to do some logic operations on it. Now, what this program will do is scan the memory of the KBus cycle task process. It will recognize the patterns and recognize where the input is being delivered from the sensor to the process, to the KBus cycle task process, and will overwrite this value. And then this value, as it will normally do, will be delivered to the PLC application, thereby changing its functionality, given that we control this input. Now, this is still executing pretty correctly. Now, let me execute the operational meltdown and see what happens here on the HMI, right? All right. Now, you see the functionality has changed completely, right? These values, they are changing violently, but the problem is that given that there's nothing to hide the presence of this alteration, the process engineer will essentially notice that there's something weird happening and be alerted. Now, if we wait just a little bit, the actual exploit will get executed, which will insert the kernel module, the rootkit, that will spoof correct functionality. Let's see what happens in the stack actually. Now, this is the stack of this here PLC application that is running. You can see the buffer with the B's, the 62 in hexadecimal. Now, this buffer has already been started to get overwritten by this value, by these here values, which you can recognize here is the start of the NOP select, is the start of the exploit. Now, at some point, these B's, this buffer will get completely overwritten by the exploit, which will in turn override some more values and, more importantly, override this value. This is the return address of the PLC application, of this function, sorry. And well, when this address gets overwritten, it will point here at the start of the exploit. And because the stack is executable, it will start executing the exploit and will eventually insert the kernel module inside the kernel. Right now, let's wait just a little bit because we have timed it to for the input to get delivered to enable this exploit. We have scripted it a little bit, so it will be good for this demonstration. Let's see. By the way, let's check the kernel if anything in any monkey business happening. There's nothing in the kernel at this point. Let's wait just a little bit. All right, it should be happening right now. It should be happening. Let's wait just a little bit. And the functionality, as you see, has been reverted back to its original. The actual functionality of the program has not changed, though. You know, the values that you've seen violently fluctuating still happen, but the HMI is being spoofed by the kernel module that has been inserted. Let's see if it has been inserted. And there's that here in the kernel. So what we've shown here is an application that essentially combines two things: altering the functionality of the PLC application itself, and then spoofing correct functionality back to the HMI, which were two main points of the Stuxnet virus. Thereby, what we have here is essentially Stuxnet in a box. And now let me hand over this presentation to Michalis for the conclusion.
Thank you, Dimitri. So to conclude, as we discussed, current PLC programming stacks allow even simple buffer overflows to hijack a whole industrial process. The fact that we have the main PLC binary being loaded in executable stack allows inputs to come in to an executable region, and then with a simple redirection, you can have remote code execution in the PLC binary, in the PLC itself, and that can result in damage to an industrial process. Second, the framework itself has a mix of proprietary and open source components, and there's no standardization in place. That means that we expect more problems to arise and more vulnerabilities to show up, since the approach to secure proprietary component will be very different compared to the approach of securing open source components. And third, on the positive side, we keep complaining how because of this IT-OT convergence, we have more attacks coming from the IT world to the OT world. We can also use that to our benefit and port defenses at the same time. And this is exactly what this talk did. So we showed how emulation and fuzzing can be used to uncover vulnerabilities on the PLCs without affecting the PLCs themselves. And with that, we conclude. Thank you very much, and we're open to questions.